Hi everybody. I guess it's 11 o'clock, so let's start. My talk is titled "How to Hack MoarVM JIT Compiler." This is the Perl conference in Amsterdam. I'm Bart Wiegmans. I work at Booking.com. Needless to say, you've probably already been told we're always hiring.
Could you speak up a little bit?
Yes. I've been told it's not amplified, so I'll try to speak a bit louder. So this talk is about MoarVM, and I thought to start out with a little bit of history. The first public release of MoarVM was in 2013. I recently learned, and I just checked, and that's for a virtual machine that's actually really young. For comparison, the Java virtual machine hotspot is from 1999, so that's 18 years old. That's what we consider mature, so we have some time to go. 2014 already, the development started for the dynamic specializer, called dynamic optimizer called Spesh, which basically improves your code as it runs. Also the JIT compiler. That was my first involvement in MoarVM. 2015, I started the project that I'm actually going to talk about today, which is the expression JIT compiler. 2016, it was still under development, and in 2017, just over a week ago, I finally opened a pull request to merge it back into mainline MoarVM, which means that hopefully you'll get the access of you'll get use of the JIT compiler very soon. I've drawn this diagram to more or less show you how the flow is from your Perl 6 program to the MoarVM system. The Recruiter compiler is itself a program that runs on MoarVM that compiles your program to MoarVM bytecode, which is then interpreted, and if it executes frequently enough, then we try to optimize it using the dynamic optimizer. And as a backend stage of that optimizer, there's a JIT compiler, the legacy JIT compiler from 2014, that tries to rewrite it as machine code. And within that JIT compiler, there's a new component, which is the expression JIT compiler. There's two things that I really want to get across with this diagram. The first of them is that it's a very long route from source code to binary code in Perl 6. And every one of these steps, the Recruiter compiler, MoarVM itself, the dynamic specializer, these have a huge influence on the quality of the generated code. And so Recruiter has gotten quite a bit faster since 2014. And I will be the first to say that that's not mostly due to the JIT compiler. That's mostly due to the awesome work that's done on Recruiter, on MoarVM, on all these levels. So I want to just say that that's where that comes from. The second thing is that the expression JIT compiler is really embedded into the old overlying system. And that has two nice properties. One, it's much simpler. Second, we can basically add capabilities to this JIT compiler piecemeal and grow it, as it were, rather than completely replacing the existing compiler. I think that's, in general, a very nice property to have for an open source project. So why did I actually start developing the expression JIT compiler? Well, the legacy JIT compiler is extremely simple. What it effectively does is take your MoarVM bytecode and one-for-one translates it into machine code. That's easy to do. It's easy to get started. But it has a few major drawbacks. First of all, it's not at all portable, because you have large pieces of assembly code that have to be completely translated, and you can't really introduce machine-specific idioms. You have to basically reinvent it for any other architecture. It's not at all suitable for optimization. Every piece is more or less isolated. It means that every piece has to load its value from memory, store them back to memory, completely independently, which is not at all efficient, because it's all this memory traffic. If you want to improve upon that, the MoarVM actually provides an unpractical amount of instructions, because what you'd like to do is then combine multiple instructions into single pieces of code. But as we have over 800 different MoarVM instructions, that is an infeasible task. That's just never going to happen. It's also proven that it's somewhat difficult to extend the JIT compiler as it is. You'd like to do something like compile specialized code for when you know the specific type of an object. If you have a specific shape of array, then you want to have fast access, and that's actually possible, but it's difficult to do because you have to use all this assembly language, and not a lot of people like writing in assembly language. So we hatched a plan. I hatched a plan. We would convert the MoarVM instructions, which are really high level. Well, it's low level from Perl 6 side, but it's very high level from machine level, to an intermediate representation. We'd add another layer of indirection, as Damien so nicely put it. It would have to, that indirection layer is called an intermediate representation. It would be portable. It would be suitable for optimization. So it would expose all those operations that are done, and it would be extensible. You'd be able to add new types of instructions based on without using assembly language. We then compile that efficiently and into machine code and run it, and that's it actually. in essence, a JIT compiler is a very simple thing in that sense. This was funded by a grant from the Perl Foundation, so I want to say thank you to the Perl Foundation. It's very awesome to help people do such work, me in this case. The JIT compiler has a number of different moving parts. Fortunately, I will not address most of them. The first is, of course, the legacy JIT, which more or less drives the process and provides a wrapper and an environment for the new JIT to operate in. It also handles all the capabilities that the new JIT just can't do yet. There's a thing called expression builder, which is the thing that translates the MoarVM instructions into the intermediate representation. This intermediate representation I call expression tree. That's not a good name, but that's basically historical artifacts. Maybe that will be changed at some point. And it does so on the basis of templates. And so it's basically aided by what I call the template precompiler. Takes templates and shapes them in a way that can be used efficiently at runtime by the JIT compiler. There's also code generation. That's responsible for selecting machine code to evaluate the expression tree that's been created. It's a very interesting piece of software. We'll not discuss it today. There's a register allocator associated that's used for making sure that every value that the program is using is actually have a place to be stored in. Also, a very interesting and very complex piece of software, much more than I had anticipated. Also will not be discussed. Assembler to basically generate the machine code, link up labels, and also not discussed here. So the only thing that we're actually going to discuss, well, almost the only thing that we're going to discuss, is the template compiler and expression builder. This is my core hypothesis of this talk. Adding a template to the template compiler and thereby extending the range of operations for the JIT compiler is a necessary thing to do for the JIT to develop further. Because without templates to feed it, as it were, the JIT is just a very complex machine that does nothing. It's also, I think, rewarding because, like I said, there's a lot of them to do. And each of these helps compile bigger pieces of code and unlocks more potential, as it were. So that's, I think, pretty fun. It is what I call contributor friendly. You can add a template in easily under 10 lines of code, and none of these lines of code are assembly or C. Unfortunately, they're not Perl either. So, but they are. I think that you'll see they're pretty simple. Now, the other thing I will discuss is debugging, because of course none of you ever make a mistake, but I do, and I find that because of the long delay or long route of code between source code and machine code can be sometimes be a bit hard. So there are numerous JIT compiler specific debugging tools that I've used and developed, and I want to show how these more or less are used. So I'll get onto the syntax of templates. Now, sorry. Yeah. This is an example. This is the basic syntax of expression templates. Some of you will find this familiar. If you know this is extremely familiar. Template is defined as a list of symbols. And a list of symbols is just an opening parentheses, a symbol, and a symbol is whatever Perl thinks is a word. Spaces in between, and a closing parentheses. And the equivalent in Perl's syntax would be that. Also the equivalent, by the way, in JSON syntax. For what I think are obvious reasons, I didn't actually use that. There's more syntax. You can have line breaks within templates. That's of course very nice for readability. You can have comments. They start with a hash sign, just like in Perl. And lists there actually started with a semicolon. I don't personally think that's very user-friendly, so I picked the hash sign. Lists can be nested, and then they basically do what you expect here. And you can have strings in them, string constants. I don't use string constants. String constants are used rarely, but they're used sometimes. An actual template is something that looks pretty much like this. Above is the source file where we have defined them. It's core.expr. A template starts with a keyword, name, and a few things. So I'm guessing this is still a bit obscure. So what I've done is expanded it a bit. As I said, the keywords, add_I, that's the name of the instruction this is a template for. What it does is it adds two integers and returns the results. Add is what we call the operator. It's some kind of terminology for it. And everything after the operator, in this case, the operands. So $1 and $2. These are the input operands to the VM instruction. And what happens is that the expression builder will provide them for you as necessary. And in many cases that will mean, if you expand them, that they will have to be loaded from memory. It's like in the interpreter. And that's basically what it shows. The local operator represents the base of register memory for the virtual machine. The address operator computes an address with an offset. An offset is not, for terminology again, offset 1 and offset 2. These are not operands, they're parameters, because these are always constant numbers, and they have to come from somewhere. In this case, the expression builder will actually fill them in. Load operator then loads yet a value from the indicated memory location. And regex indicates that the value that is being loaded is of the same size as a VM register. So this basically loads the value from the VM memory into the wherever the JIT compiler actually needs them. We can even go a little further with that, because as I said, add_I yields value. This value has to be stored for consistency into VM memory again. And in virtually all templates you'll see, that's completely implicit, because the expression builder will introduce this store operator by itself. But in this case, I've shown that you don't actually have to do that. You can add an exclamation mark, and that means that the expression builder will not insert the store, so you'll have to insert it yourself. The $0 thing, that's an output operand. And unlike the input operands, which are always provided by value, the $0 is always provided by reference. So it's only the address part with local. It's not any load associated. So I think you can see now that from even this example that this expression, language as I call it, is very low level. So memory operators take a very prominent role in it. You've already seen load, store, and address. And on the right hand, I've shown basically the C equivalent. I do hope most of you kind of make sense of it. The new one here is index, which is used to compute the offset of an element in an array. This maps, by the way, directly to an equivalent machine language instruction, so that's actually really cool. There's also copy. That doesn't do anything, but it is used in code generation, so it's sometimes seen in templates. So let's move on to a slightly more complex template. This is getWhat. Not sure how familiar all of you are with Perl 6, but what is the method that gives you the type object of an object. So for instance, 42what, that's the and what I've shown here are the use of list macros. And list macros is everything that is something that starts with a character and a symbol. Now what happens to a list macro is that you define it somewhere, and then the expression compiler will insert that into the list you've created. So this is a macro to access a field from an object. It looks kind of weird. The comma things are the things that are substituted into this list, and when that substitution is done, it's basically substituted into the outer list. And the C equivalent of this would be cast to a type object and then access a field. There's also something else new, which is the ampersand list. The ampersand lists are what I call parameter macros. Why are they called parameter macros? Because at pre-compilation time, they will be converted to C macros, like this offset of standard macro, which gives you the offset of a field in a structure. And the C compiler will then convert that into a constant parameter. So effectively what this does here is that it will get you the offset. It will allow you to compute the offset of an object using the field in a type. If we expand the list macros in the getWhat macro, then you'd see that first of all, the list would get much longer, the templates. And it's also, I think, considerably more difficult to see what's going on, and it's considerably easier to make a mistake. And if you expand or replace the parameter macros with the constant values they represent, well, it definitely does get shorter.
Which is good.
But it's just a few too many magic numbers, and not really robust against changes. So I kind of hope you see that these.
Also, it's architecture dependent again.
Also that, yes, very true. So I kind of hope you can see that that these macros are there for a reason. I hope the syntax doesn't confuse you too much. If the names don't. Now, obviously, MoarVM has to represent conditionals. This is the branching operator, one of the basic branching operator. It will go to another place in the code if its argument is non-zero. And that's implemented more or less as this. When is the unary or single conditional. It has no else block attached to it. Branch is the equivalent of goto. And z is non-zero. So I think this is this map's reasonably straightforward. However, there's something hidden here that you can't see at all, but it's very important. Still, there's a type system here. See, when I showed you the templates for add_I, nearly everything you would see nearly every operator would yield a value. And when the if statement doesn't yield a value, and goto statement also doesn't yield a value, and a label is strictly speaking not a value. The Boolean that is returned by nz is a value, but it's not like a value in the way that the result of an addition operation is. A Boolean results into a flag. It's not really interesting to know what goes behind that, but the important thing is flags don't fit into general purpose registers. Most other things do. That's why the type is called reg. Some other things don't yield a value. Again, you've already seen store, you've seen branch. And then there's cargs, which is a special type to represent the argument list to a C function. I'll get back to that in a few slides. Of course, having a type system means that you have to convert them. And there's a few operators to do that. Discard, make sure. Discard basically translates a register to nothing, so it discards it. The reason to have these is mostly to aid in code generation, because compiler cannot find any code for mismatching types. It just doesn't do it. In the past, the templates would not be type checked, but I'm happy to say that currently they are, because otherwise you're basically doing the equivalent of writing assembly in Lisp, and it's not a very happy experience to have type errors in that. So
you have experienced that.
I have experience with that, yes, very much. So these days we do have a type checker, and you don't have to worry about it because it will tell you if it's incorrect. Instead of blowing up at runtime, which is less fun. With more conditional operators, there's if. If yields a value, it's more or less equivalent to the Turnier operator. There's also if v, not shown here. It does not yield a value. Hence the v for void. But there's also something else new here. That's the let statement, or keyword. And what that allows you to do is declare local variables. Cool thing about that is they're actually value names. They're not variables because you can't store anything to them. The let values are always computed prior to their use in the expression that precedes them, which is really handy because you can otherwise it becomes really difficult to accidentally avoid the referencing a null pointer. So you kind of need these things to have. Finally, in conditionals, we have the chained conditionals like and or, except in the expression language we spelled all, and they can take any number of conditions. Turns out that's actually simpler to do than a binary operator, because it's more regular to compile this way. So, like the C and Perl and whatever equivalent, they short circuit. So they stop evaluating code when the first failure or positive match in the case of OR is found. That's also handy because that's also a way you can prevent referencing null pointers. And again, the equivalent of OR is any. So I hope that should be simple enough to do. If you need more ordering guarantees, or you need to have a template that does more things at once, then you can use a do block or doV. doV does not yield a value, do does. And this is a thing that writes a reference to another object in an object. And MoarVM uses a generational garbage collector that implies that the old generation objects and young generation objects are collected separately, which in turn means that if there's a reference from an old object to a young object, that the scan of the young objects will not find it. Which in turn means that if we do not maintain that reference somehow, and we do not explicitly list it in the garbage collector, we will forget that there's an old object referencing a new object, and we will destroy it while there's still a reference, which is not a good property of any garbage collector to have. Which is why there's a write barrier macro. So we first add a write barrier, which does the necessary checks and adds necessary references, and then, only then do we do the write. So, finally, there's function calls. I already alluded to these. I should say virtually all functionality in MoarVM is actually exposed by means of C functions, amongst which, of course, Unicode stuff is there. So there's operators to do that. Call V and call. One yields value, one does not. Guess which? The func macro, which substitutes this with a constant pointer to this function. Yes. Arglist is the operator that sets up the function arguments so that they are in the correct place specified by the platform. And carglist wraps an operation or wraps a value and specifies how it should be passed. So I showed you the type system table just a few slides back. And what's interesting here is that we now start making a distinction between integers and pointers, because on x86-64 it doesn't actually make a difference, but in other platforms it does. So we try to maintain the distinction. The other final thing to show here is the TC operator. TC refers to thread context. It's basically a sort of global object that all sorts of internal virtual machine state hangs off on. And most MoarVM functions actually use it in some sense. And that's actually all there is to it. It's not really a very large language. It does have a number of limitations, of course. It's very low level, as I've shown you. It looks like Lisp. If you try to do Lispy things, it will not work. It will blow up. There are no looping constructs. This is a major limitation because it restricts severely what you can express with it. You can have branches, you can have labels, so you can actually implement loops, but you can't express them. There are lots of things that are still missing. I think we have about 40 operators. Much more will have to be added to expose various functional pieces of functionality. One of very important is floating point support. floating point support is actually a bit difficult because floating point numbers have to be stored in different registers from general purpose values. And so that's adding floating point support complicates all other design aspects, so I left that out for the minute. There's very few bit operations implemented. There's all sorts of interesting stuff that we just don't have yet. How am I doing for time? Okay. Other restriction, as of yet, it can only handle single basic blocks. Now, I expect not all of you to know what a basic block is, but it's a very rudimentary unit of code. And this means that the expression compiler can only compile pretty small pieces. I have plans to extend that and do multiple pieces and do entire frames, but it will take some work to do that. So again, that's all there is to show about the expression compiler. But that's not all I will show you in this presentation. Again, debugging is really essential because if you're anything like me, you will make mistakes, and these will be in very remote places, and it's a vast surface area to look for. There's lots of code that's being compiled. There's lots of the compiler itself is also it's a few thousand lines of code, which isn't that bad, but it's still a lot if you want to go dig through it. So what I'd like to do now is take you through a hypothetical debugging situation. And it's not so hypothetical because what I will show you is basically how I debug things. It's based on a true story, as it were. Suppose I have a nice Perl 6 program. And suppose that one of the things that it does is crash with a segmentation fault. Now, I think that's actually pretty good news usually. Because a segmentation fault is a much clearer indication that the VM is wrong than, for instance, a missing attribute access, which might mean your program is wrong. So if there's a segmentation fault, that's basically when I can start working. So the first thing I always do is check if this works with dynamic optimization is disabled. And you may recall I showed you on one of the first slides a diagram where the JIT compiler was embedded into the dynamic optimizer. So if I disable with this environment flag the dynamic specializer, then the JIT also won't run, and it will actually, and in this example, that will actually solve my problem. So that's good. Suppose, well, I counted yesterday, and even when I say that this is only a problem in either the JIT or in the specializer, then we're still talking about 20,000 lines of code, which is still a bit much. So I can also drill down further. I can also leave the specializer runner, but disable just the JIT compiler. There's another environment flag for that. And let's suppose our program still runs. So this is good. Now we can be fairly sure that this is a compilation error. And we can dig even further, because, as I said, the expression compiler is in fact embedded into the legacy JIT compiler. And so I can disable it separately, in which case everything that would be done by the expression compiler will now be done by the legacy compiler, and suppose my program now still runs. So that means that I've drilled down from what is over 100,000 lines of code to only a few thousand. So that's actually much better. And we're fairly sure that's a compiler bug. And compiler bugs have one nice feature. If there's a bug in your program due to a compiler bug, that's because the compiler emitted some wrong code. So the next thing to do is figure out which code that is. And in single-threaded programs, which is still the majority of programs that I write, it's actually completely predictable in what order, or not predictable, but deterministic in what order some pieces of code get active and then get compiled and are basically sent off to the JIT compiler. And recently we've had a change to JIT compilation and specialization on another thread. So in this case, the special blocking thing will force the program to be single-threaded, thereby force the program to be deterministic, indeed. So if I have a deterministic order, then I can identify each piece of code by giving them a sequence number. And between two runs of the programs, they will stay the same. And if I have that way to identify, I can say I want the expression compiler to stop working for exactly this piece of code, which is then what happens, which is what this MoarVM JIT expression last frame flag is supposed to achieve. And now in this case, I can see that between frame number 1 and frame number 1000, somewhere there is a mistake. Now, most of you will be programmers, virtually all of you. So,
binary search.
Yes, exactly. You can now see the range coming. And of course, there's a program for that. Because, yeah, I'm a programmer. And I'm late.
That
So,
explains a lot.
yes. Yes.
Can't we somehow capture the stream of commands that is sent along and just read them all? That's a nice thing about compilers. They always talk about what they do.
Actually, I'll get to that in just a few slides. Well, thank you for saying. Although, I should say, that's by itself not as useful as this. I think within a certain piece of code, a subroutine, we use the terminology frame. There is actually there's the basic blocks. Basic blocks are also numbered, so I can also bisect on the space of binary numbers or the basic blocks. Of course, at first I don't know how many frames there actually will be compiled, so I use exponential probing to figure out when the program starts crashing or failing. And once I have that, I would like to see what is actually the difference between the JIT compiled code that is right versus the JIT compiled code that is wrong. And because I've now pinpointed it to expression compiler, and because I can disable this expression compiler very locally, I can use this program, JIT_dump, to get two different dumps of that piece of code, one with expression compiler enabled, one disabled, and it will list them. So now you want to compare these. These are by the way, binary dumps. So you want to use a program like objdump to convert this into machine code, or not machine code, assembly code language, which it probably makes a lot more sense than a binary itself. By the way, I just want to speak out my appreciation to the Strawberry Perl folks, because they have in their infinite wisdom shipped objdump in Strawberry Perl on Windows, without which Windows or the expression JIT on Windows would not have happened. So, so this, you can read this. Big disadvantage of objdump output is it prefixes every line with the hexadecimal address. And that means that even if one offset changes anywhere in the program, everything after that will also be different. And a program like diff cannot tell you what the actual difference is. Of course, there's a program for that as well. And it basically mangles the objdump outputs and ensures that labels are consistent and comparable. And I wish I should have shown you basically the diff output between these two pieces of code, because That would have been nice, but you have to take my word that this is a really much nicer way to look at the diff. And here's what when I get to what you were just referring to, there's a JIT log. I'm currently not super happy about what it does because it's very ad hoc. It basically prints out statements as it comes by them. That means that somebody who intimately understands everything can figure out what happens. But I want to move to a bit more structured thing. One of the cool things that it does do is it dumps something called the GraphViz tree or graph of the expression that is being compiled, which I just show you a tree for set and go to. That's actually what this is. And so this is another way to represent the code that the JIT thinks it's compiling. It also has other things, but yeah. These two textual forms and graphical forms are completely equivalent. If you want to dig even further, I don't expect, to be honest, I don't expect many of you to come to this far. I don't use this actually all that many. But if you want to go even further, you can instruct the JIT compiler to set breakpoints at a specific piece in code, a specific start of a basic block. And that's what MoarVM JIT breakpoints does. You can set multiple, they'll be separated by a colon. If you will then run it under a debugger, the debugger will stop exactly at that piece of code, and you can basically then inspect registers and step to instructions. And if anything, that should be basically the final recourse to figure out what's actually going wrong. But again, I don't even use this all that much. Unfortunately, it doesn't seem to work very well with GDB, but you can use LLDB and it will usually do precisely what you mean. And it has an interface that's actually very similar, so that's pretty cool. So, I'm actually on time. I'm surprised by that. In conclusion, I've shown you how the JIT compiler more or less works. I've shown to you how you can add expression templates. I've argued why that is necessary. I've argued why I can show you how you can actually debug errors and make sure that you're doing things right. So please come help me write expression templates. We need about 700 more. So, and we will be needing more of these still when we start creating specialized templates for object types. So, yeah, there'll be plenty of stuff left to do, and I think it's great. I hope it's a great way to start and make this into a community effort. Thank you all very, very much. Do you have any questions? Yes?
So the current expression templates are mapping, to see if I'm correct, a single MoarVM abstraction into intermediate representation.
Correct.
Okay. And do you have any plans for things like optimization of the intermediate representation, SSA
Yes.
form, and so on?
That's actually a good question. So there's two things there. First of all, the question is, do we have any plans to optimize this intermediate representation? Yes, that's what it's designed to do. Every single value, every single basically node in the expression tree represents a single value, so it's already in SSA form. There's only a limited number of them, so you can usefully say you can usefully match patterns and do intelligent things. So yes, that's very much in plan. I have plans to do common subject expression elimination, all sorts of fun things. But for now, correctness has taken precedence over efficiency, but it's definitely the first thing one of the first things I'll be doing. Yes?
So which kind of functions can be best optimized using this method and which can't, and how do you, because our op list shows the different input and outputs, right, and the different if they're in 64s or whatnot, and what the output is. So does it take that, or is it only useful for certain kinds of functions?
So your question is, if I can understand correctly, for which instructions this is suitable or not?
Yeah.
Ultimately, for all of them. Like I said, I don't have floating point support of them, so that rules a bunch of them out. But ultimately, all of them will be converted, and we do in fact use the information in the op list indirectly because it's part of the intermediate representation that this works on. But yeah. Yes.
Thank you. Can you please clarify a little bit? I mean, we have another kind of intermediate layer called NQP. What is like the work division between NQP and this layer?
That's actually a really good question. So the question was, we have another intermediate layer called NQP, and what's the difference between this and that? To be fair, I think that NQP, it sits much higher up the stack, and it's not actually an intermediate representation. It is a tool to build the Recruiter compiler. It is itself a program to the Recruiter compiler, but at the moment that you're actually executing, I have to stop very soon. But long story short, NQP is itself a program and a language, and it's not a representation as such. And this is. And this will be the last question. Thank you all very much again.